Hello, I am Syntax Sugar, and today we'll be covering the normal distribution. So, uh, I'm sure you've seen the normal distribution in some shape or form, as it's usually used in a lot of figures, and even those that don't know statistics would know what it looks like. And here you may see that there are a bunch of different normal distributions. So, what makes these normal distributions different? And these are the parameters. So, for the parameters of the normal distribution, we have two parameters, and these are the mean, denoted by the Greek letter mu, and the standard deviation, denoted by the Greek letter sigma. And with these two parameters, we define the probability density function as like the normal distribution isn't drawn arbitrarily. We use mathematical formula for it. And you can see here we have the sigma and we have the mu that are able to define our function. And the standard deviation roughly represents the spread, and the mean defines the center. So if we go back to our line, we could see here that the one with mu is equal to 3 is the one going centered a little to the right of the rest of them. And you can see this one, it has a low spread. If you can see, it has a standard deviation of 1, which is the lowest of them all. So it's centered like at the mean. And how do we actually calculate probabilities from density functions? For calculating probability, we want to calculate the area under the density function, as it just gives a weight to the density function. And we can do this using integrals, because if you're familiar with that. But the normal distribution actually doesn't have an antiderivative of regular functions such as like x squared, x cubed, sine, cosine. So we can only estimate our values. And before computers, uh, if you had infinitely many parameters and parameter settings, it would be impossible to do that. So they used to make use of a z-score. And what this z-score is responsible for is that it's able to like convert the value you have, the observation you have, distance from the mean to kind of how far it would be from the standard normal distribution. And this allows you to only rely on this, and you could create a table such that all scientists could use it if needed. But as computers have came, you're not really like limited to this method. But it is a very standard and practical way to do it. So let's do a question. Imagine Harry Kane shooting a shot, and Harry Kane's shot speed is normally distributed, and we have a mean of 90 kilometers and a standard deviation of 15. What is the probability that Harry Kane's next shot will have a speed of less than 60 kilometers? So the numbers here are just estimates, so don't really look into them. So how would we solve it? We take the mean of 90 kilometers per hour and the standard deviation of 15 kilometers per hour, and we're able to construct a normal distribution. And x is normally distributed, so we use this sign. Oh, yeah, we use this sign. And in this, we know that the probability that x is less than 60 kilometers per hour is the integral from negative infinity to 60. And this is how you're able to do it. And you can use a calculator for this. Most calculators have the normal function built in, and you'll be able to do it without looking into the integral. And it will approximately be 0.0228. So the conclusion in terms of probabilistic and a statistical statement would be that over many repeated shots, the proportion of shots that will have a speed of less than 60 kilometers per hour is 0.0228, which is very rare. So you'd expect shot going faster than that most of the time. And the use of normal distributions is really widespread, and it can be used to describe many different phenomena from very different fields, like sociology and mathematics, obviously, and engineering. Students use it to describe how things are manufactured. And it really is important to understand what it means and get a conceptual grasp of it to be able to calculate probabilities from it and use it for any statistical test that you might or experiment that you might have. And that's all for today. I thank you for your listening, and bye bye.